today, this wonderful conference. We've got Nir Lazarovich talking about finite index rigidity of hyperbolic groups.
Thanks. Thanks. The invitation. Yeah. So we all know what hyperbolic groups are. I think it's maybe the first time I don't have to do hyperbolic groups when I give this talk. But finite index rigidity is just a fancy name for the following property. So maybe that's what we'll start with. So the definition is we say that a group is finite index rigid if it does not contain two isomorphic finite index subgroups of different indices. So I'll just write it like this. If A and B are, so this will be finite index subgroups of G. If they are isomorphic, then they have the same index. Okay, so this is also called this satisfies the volume condition. It's in your paper. This is why I'm looking at you. Satisfies the volume condition. But I felt like this is less fancy than saying something, saying rigidity, right? We all want to prove rigidity results, right? The volume condition. Okay. Yeah, good. So let's start with maybe an example or maybe a non-example first. A non-example would be the first group we learn about Z. Right. So Z is not finite index rigid because I don't know, something like this. Right. So in index 2 and index 3 subgroups can be isomorphic in Z. And the same holds for anytime I take a direct product in Z. I have the same problem. Okay. What about examples? Maybe examples are more interesting than the non-examples. So maybe the first thing is finite groups. Okay, boring example. You can figure out why they're index rigid. Maybe a slightly more interesting example would be the free groups. Yeah, so let's actually prove this just so that on the same page, you know why they are finite index rigid. And also because the proof will be sort of the main idea of all of the following examples. Yeah, so the idea is the following. If you have a finite index subgroup, then we know that the Euler characteristic of A is, well, the Euler characteristic of Fn times the index. Okay, so we have this invariant which is multiplicative, meaning satisfies something like this with respect to the index. And so since this invariant is non-zero, we get if A is isomorphic to some B, again a finite index subgroup, then they have the same Euler characteristic. Right. So here I'm using the fact that this invariant is really a group isomorphism invariant. Okay. And since this is not zero, use multiplicativity to deduce that they have the same index. Okay. This, I mean, I wanted to write it down just so that it's on the board, but I'm sure all of us knew this result, right? But then we see that actually there was nothing too special about the free group. It was just about having this multiplicative invariant, in this case, the Euler characteristic. So for instance, surface groups, right, also fit into something like this, and any group with where the Euler characteristic is non-zero, right? Great. Yeah. So any more examples? This is the result of Tikiotis. So a group, so G with infinitely many ends is finite index rigid, and G with some surface or quadratically hanging piece in the JSJ. So let me write non-trivial JSJ, but really I mean that there is a surface. Okay. Yeah, so the next one is, I think, Reznikov. Groups with with efficiency at least 2. And maybe more general. So I think generalizing this and this is what? They have Euler characters. Okay, fine.
Same thing.
Yeah, but yeah, I think the okay, yeah, fine. Sorry? The Euler characters together, the efficiency will tell you something about the Euler. Right. So yeah, I think the point here is that the rank is I mean, you can make the rank into a multiplicative invariant, but that's right. But more generally, you can have groups with a non-trivial, some non-trivial L2 numbers. They are also multiplicative with the index. You can play the same game again. And okay, and now maybe a more serious example is maybe lattices in simple E groups, or irreducible lattices in simple E groups without fractals. Yeah, E groups. Right. So here we actually have like rigidity. With most so. Yeah, but again, one can, I mean, reduce this to just saying that the volume is a multiplicative invariant, right? Okay, it's much less than what this is actually saying, but let's see, you get it's not, and yeah, and then Wang and Wu saying most three manifold groups. So maybe this is for the next conference, but yeah, so basically not without covers that look like this. That's the okay, good. So yeah, so the main theorem, where do I want to put it? Yeah, let me put it here. So the main theorem is that hyperbolic groups are finite index regions. Okay, so for this I have to exclude this one annoying example. So all non-elementary hyperbolic groups are finite index. And note that I'm saying non-elementary, but finite groups are fine. Okay. So maybe let's call it theorem A. And let me maybe put this maybe first a corollary before I put it in context. There were a lot of talks about out Fn. Maybe give the following corollary. So if I have an autoroidal automorphism, then the following mapping torus of phi to the n is isomorphic. Oops, they are isomorphic in means K and L have the same, right? So I mean, yeah, okay. Yeah, so why is that? They're hyperbolic, those are finite index subgroups. K is the index of this in Fn semi-direct product phi. So yeah. Okay, now let's maybe put this in context. So maybe the first thing to say is that one-ended groups. So Sela proved that one-ended groups are co-Hopfian, meaning the group cannot be isomorphic to any proper subgroup, right? So right, which in particular means the group itself cannot be isomorphic to a finite index subgroup, okay, which is some sort of this kind of rigidity. One cannot be equal to hyperbolic. Yeah. Thanks. All groups are hyperbolic, really, right? Sorry. Or maybe relative. I just don't want to offend anyone. Yeah. Good. Yeah, but I think more surprising is this result of Emily and Daniel. So there exists a group G with subgroups which are isomorphic but have a different index. I'm always missing the something. One-ended, hyperbolic. So there exist isomorphic subgroups of different indices. And now you might ask yourself, I mean, wait, what's going on? Yeah, exactly. Well done. I didn't put a little dot. So one of them is infinite and the other is finite. Right? That's the point of this. Okay. So somehow this sort of fills the gap that's missing in the study of the possible indices of. Sorry?
You don't say one.
Yeah, free groups are. Yeah. Good. So really the idea is to follow this line of proof. And yeah, so just write it. So maybe so some function from all groups to the R is multiplicative if I have some finite index subgroup of G, then this will be multiplicative in the index. So okay, so the goal is really to show that there is such a multiplicative function that for all, say, non-elementary, actually will prove one-ended hyperbolic groups. It's non-zero, right? This is what we need. Oh. Do I want? No, I want the index on the other side. You mean? No, this is the right. Yeah, the same. It's the same, right? It's going up as the index grows. Yeah, good. So now we're ready to start maybe coming up with this invariant, and this has to do with complexity. So it's the next. What? That's right. But actually, it's like, yeah. I mean, it's true. The index is the volume, so that's the right answer. But as I said, sounds less fancy. Which volume condition, right? Okay. Good. So here's the definition. So I'm gonna take the stupidest possible definition of volume for simplicial complex. Okay, so I have this is some simplicial complex. I'll just define the volume of K to be the number of simplices, all dimensions. Okay, you can define finer things like asking only for cells up to dimension something, right? But let's just take this as our definition of volume. Okay? And now let's define the complexity. So this is the volume. We should underline definition. So volume, 1. Good. Definition of complexity. So if G is a group, let me assume of type. I'm really secretly assuming of type F. Then the complexity of G, the topological complexity, which I've been told has different meanings in the literature, but this is the right one, is the minimum of the volumes of simplicial KG1s. Okay, so the volume of K, where K is a simplicial KG. So classifying space for the group G. Okay, and I insist on putting simplicial because I really want to count also how complicated the cells are, how complicated the attaching maps are. Yeah.
So you're counting all the simplices in every dimension?
Yeah.
Okay.
I mean, okay, I'm actually what I'm doing is I'm not looking at classifying space because not all hyperbolic groups are of type F, right? They have to be torsion-free to be of type F. So what I'm really doing is I'm only looking at things that are connected for big enough number. And actually, I only need to count cells up to dimension 2 in those. But I need them to be simplicial with respect to the bigger. And so let's not bother ourselves with this. We'll just assume all groups are torsion free. Fine. Great. Okay, and here's the actual theorem that will prove. So theorem B says the following. So take a one-ended hyperbolic graph. Yeah, and so there exists some number that depends on this graph, such that for all torsion free, okay, so I'm putting torsion free just to have type F, but really you should remove it. So torsion free group acting on X freely co-compactly, we have the following. So the complexity of G is related to the volume of the quotient. Okay, so if you want the co-volume of G. Okay, so this is the actual result that we'll be proving. And yeah, let me just say that from now on, I will not write all of those constants. So anyone who needed to copy this, I'm going to change it now. Okay. So I'm just going to write. Okay. So this means exactly what was written before, with a constant that depends on X. Great. Okay, and here's the corollary of it. So maybe let's call it C. G, say again, torsion free, but really one does not need it. One-ended hyperbolic group now. Okay, then for every finite index subgroup, we have that the complexity of the subgroup is related to the index. Yeah, so what I would like to show you now is how to go from B to C to A. Okay, and then we can focus on the real thing, which is theorem B.
When you wrote that X in theorem C, was X G or
sorry?
no X?
Ah, yeah. Right. Okay, so yes, going from theorem B to C is quite easy. You can, I think all guess what's coming. So okay, so why does B imply C? Well, just take X to be the Cayley graph of G. Right? To take X to be the Cayley graph of G with respect to some generating set. This will be, I mean, if G is one-ended hyperbolic group, this will be a one-ended hyperbolic graph, and all of the finite index subgroups will act freely and compactly, and the volume that you see is proportional to the index. Right? So volume of this X mod H is now the group acting, the finite index subgroup, is proportional to the index. Okay, and you get the result. Okay, questions? Why does C imply A? So here there's a nice trick of Reznikov. So we want to find a multiplicative function. So this is, yeah. So what we'll do is we'll look at the stable complexity of the group. So define, let's call it nu of G to be the lim inf over finite index subgroups. So here I'm doing a lim inf on the lattice of finite index subgroup of the complexity of H mod the index. Right. So maybe it's an exercise to prove that this guy is multiplicative. Maybe what's not clear in general is that this is actually is finite, but okay, but it is if the group is of type F. But what's more important is that from theorem C, we see that for one-ended hyperbolic groups, so if G is one-ended hyperbolic, then this is non-zero, right? Just because there is this lower bound on this ratio. Okay, and so we get theorem A for one-ended groups, but this is actually all we needed, right? So we had this result of Sikiotis telling us that infinitely ended groups are finite index rigid, and okay, 0 and 1 is not included in the theorem. So yeah, sure.
Right. So to get this to work, you need theorem C without.
Yeah. So you want to know what's the right thing to put there?
Yes,
Yeah. So the right thing is to define. So I hinted on this. Like you define complexity. So you write I and M. Okay, to say same thing. Okay, so you minimize over something. You minimize over simplicial complexes, which are M connected. Let me think for a second. M minus 1 connected and M dimensional. Simplicial. Yeah, so M minus 1 connected. What do I want to say? Maybe M minus 1. Okay, let me do. Yeah, M minus 1 connected and M dimensional. Okay, and with a free G action. Okay, and you're looking at the volume of this X mod G. So maybe let's call it the universal coverage just to feel better with ourselves. But actually, you're not counting all cells. It's enough to count up to dimension I. Okay, so this. And yeah, and then the right thing to put there is C2M, where M is big enough. So big enough could be, for instance, the asymptotic dimension of G. So, but it could be actually lower for certain groups. So yeah, but this is actually, I mean, maybe a little bit about those invariants if we're already opening this up. So this is just the rank, right? You're looking at connect. I mean, I hope I wrote this correctly, but should be connected graphs. Okay, and
It's not because it's
Hmm?
oh no, sorry, this is
yeah, can take barycentric subdivision. It will be also simplicial downstairs if you. Is this what you're?
like
Yeah. Okay, so this is like the rank. Rank is not good enough to differentiate different groups. So this is definitely question. The next one is maybe C. Let me write C2 It's basically the same as C1 2 if it's one-ended, I think. No, it's not. This is basically the Delzantian variant. Delzantian, which is so for, let's say, for one-ended groups, it's roughly the same as the Delzantian variant. What is this thing? You take your presentation, you're counting basically the length of all the relations. You sum the length of the relations, more or less. Okay, this is thing, and you minimize over all presentations. You get this. This tells you how complicated your group is in terms of its presentation, right? And I don't know if theorem B, C work with the Delzantian variant. I think this would be very interesting. So you put it here as a question. Can you replace C with the Delzanti invariant. So let me actually call it by, it's called T invariant because it's denoted. Okay. Yeah. It's a directed set downwards, right? You take limit. It's some soup of inf of blah blah blah. You're thinking about why it's multiplicative.
By having being isomorphic. Like I was just thinking that this was
Yeah, that's a good point. Maybe I should have said it. This is really a group isomorphism invariant, right? I mean, did not depend on the action on X. So that's really the strength of this theorem, is that on the left side you have something that depends only on G, while on the right side you have something that depends on the particular action you chose, right? But okay, but the constants here also depend on the X you chose. So really it's only useful when you sort of, you have your one space that you want to understand, okay? Could be the big group in which the finite index subgroups are, or it could be whatever, the Bourdon buildings, and you want to understand lattices in Bourdon building, right? But you have this one space that you want to understand, and then there is this relation of groups that act on it, the complexity of the groups that act, and the core volume in this action. Okay.
So theorem C implies theorem A, hyperbolicity is not used, right?
Right. Yeah, you just need to, yeah, this trick, like once you find a group invariant that sort of behaves like the index, not multiplicative like on the nose, you can apply this Reznikov trick and get something that's actually multiplicative. This is all this does for you. Yeah, and this is the multiplicative invariant that Emily referred to in her talk. You're tired. Tired.
So is it true that if you fix I and increase M, CIM stabilizes, or is it just?
I think it shouldn't in the.
Okay, but there exists an M that's big.
There exists an M, yeah. So per X, there exists an M that you can apply this for.
Okay.
Maybe this is the same question. Why didn't I just take the I skeleton on
the I skeleton off?
Just soft fast.
Yeah, so the word simplicial is important. No, but the thing, I mean.
Yeah, why have M? Why not?
No, but when you, I mean, yeah, when you take, you're thinking of like an infinite classifying space, right? Infinite limits. But to make this into a simplicial object, you must insert more cells of lower dimensions. I don't think it's just, it's well defined. That's the, right? And it's not a CW thing. It's very important to note that this is not, you cannot just take CW simplicial complexes, even for a surface, say, right? When we look at, no, a surface is actually good. Okay, maybe let me not try and find an example on the spot, but yeah.
Okay, so the actual statement that to answer Dave's question of theorem B is, given X, there exists an M. So that this is true. C2M.
Yeah.
Okay.
Yeah.
We don't know if that M is like a group invariant or anything interesting.
The M that we should take there?
Two, right? It could be two.
It could be two, and it's often the case that it's two. What you really need is some non-trivial check homologic class in the boundary of the group. That's what I'm hiding. Okay, now let's, I mean, so the rest of the talk is, I want to take you through some of the ideas of the proof. So really what's left is theorem B. So, right, so that's our setting. We have our one-ended hyperbolic graph. And we have a group acting on it, and we want to relate complexity of the group to the core volume. Okay, and the first ingredient is the Mineev bicoming. So the first ingredient is Mineev bicoming. Here's bicombing. What is this terrifying thing? Wait. No, I wanted to start with something simpler before. Sorry. I apologize. We'll postpone the scary stuff for later. I want to start with an observation that there is an easy inequality there. Easy inequality. And the easy inequality is that the complexity is bounded from above by the volume. Okay, so why is that? So complexity. The reason is I can replace X with some contractible Reeves complex. So replace X with a contractible Reeves complex with R. Okay, note that I did not really change the volume. I mean, G still acts on this thing. Okay. If the thing was torsion free, it would be a free action. I mean, can really just replace X with one skeleton of the Reeves complex. And what's more important is the volume changes, but in a way that depends on your X. So really this. Yeah. So okay. Now let me say why does it help? So the point is that the volume of X mod G, right? So this is basically the same as the volume of R mod G. Okay, so I added cells, but I added them in a way that that is controlled. Okay. And okay, but what's written here? I mean, this is a contractible space modeled out by a free group action. This is a classifying space for G. The KG1. Okay, so this bounds from above just the complexity of G. Right. I mean, this is really the direction. And let me say, I mean, theorem B, like this kind of the idea of relating the co-volume of a group to some complexity of the group, that's something that's been done, I mean, a lot in the setting of smooth X's, right? So when this is, say, a locally symmetric, a symmetric space or something, right? And in those cases, this is actually the inequality that most people focus on. Okay, and it's hard. But here, the simplicial setting is this inequality is actually an easy one. Okay. Good questions about this?
The non-trivial check per one person of Andrews coming from the one-ended hypothesis and best being less or something.
Yeah, I mean the one you don't need the one-endedness there. I mean you can. I mean if it's not one-ended, then
If it was free.
What? Sorry.
If it were a free group, you'd be in trouble.
I mean just in dimension 0 you have.
Oh, you're okay. Dimension 0 make happy. Okay.
The thing is you'll see. I mean I don't know if you'll see, but it will show up at one point. But okay, so now we're ready for the scary stuff. There's bicombing. It's actually not that scary. So let me try and convince you that it's not as scary as you might think. So here's I've proved. So X is now a hyperbolic graph. Assumes that there is a group acting freely on the graph. Actually, freely and co-compactly. Actually, it doesn't really use the fact that it's free. You can take G to be out of X as far as no. Yeah. Then there exists a bicombing. So there exists a function that's denoted Q from X times X to one chains, let's say with Q coefficients, satisfying the following. So first of all, it's a bicombing. So I want the boundary of Q of XY. Maybe I should say this. I'm really thinking of X as being the vertices of X. And here I'm thinking of x being the graph. Okay, so it's a function from pairs of vertices to one chains. And I want the boundary of something like this to be y minus x. Okay, so maybe I'll do a little drawing here. So here's my x, here's my y. Really, I'm thinking of it as sort of the simplest thing would be to take a path, but maybe I want to take something like that, right? Okay, so this is one. The second thing is I want it to be antisymmetric. So this form. Yeah. Okay. It should be equivariant under G. I hope you can differentiate between G's and Q's. Not sure I can. Okay. And now are the important assumptions. So it should be quasi-geodesic in the sense, so Q of x and y should lie close to the geodesic from x to y. So in some neighborhood, the support of this should be in the neighborhood of the geodesic between x and y. And that's a good opportunity to introduce the notation of delta. So whenever I write delta on the board, it's a new constant that depends only on x. Okay, it's not the delta of hyperbolicity, just a new constant dependent. Yeah, such a useful thing. So just to be sure, there are delta many points in a ball of radius delta. Delta plus delta is delta squared, is delta. They're all different constants that depend on your x. It's fine. Okay, good. Right with this. The last thing is we want bounded defects. I forgot something here. It's actually not a necessary assumption, but it's in Mai-May, so I'll edit the one norm of this. So you just sum the coefficients is bounded by delta times the distance between x and y. Yeah, and the last thing is the bounded defect, which is really the really what we want, and sort of you can think of this as sort of generalizing the hyperbolicity. So this is where it comes in. So the bounded defect. So for every x, y, and z, I want the by coming from x, y plus y to z plus z to x to be bounded. Okay, so really what we should be thinking of is, this thin triangles. So let me each time I'm writing a bicoming, let me just write a path and see what this says. Okay, and we'll see it's actually much stronger in this. So I have a path from x to y. No, so I chose them so that they should cancel. Good. So I go from x to y, so all the arrows should be oriented in this way. And what I want is for most of it to be canceled with, or this part to be canceled with going from y to z. Okay, so really the bicoming from y to z can go in a different way, but I have a bound on how many times this happens or how much this happens. Okay, and the same for here. You see, so all of those things cancel. Again, I'm thinking coefficients are always 1. They're not. They're in Q. Okay, but and so you're left with a bounded defect. So this amount of bounded defect should not depend on x, y, z. It depends only on x. That's the meaning of delta, right? So this is the questions about. Excellent question. Excellent question. Yeah. So this is So I mean, I don't know if it's exactly the same thing, but there's this notion of globally stable cylinders, very much related to this, and it's open whether all hyperbolic groups have globally stable cylinders.
So could look at the GS as Y and a GS as a one gene. Does that have bounded deficit from U and Y?
Wait, from? So choosing it, that's exactly the point here, right? You can, I mean, to satisfy 1 up to 4, you can just take geodesics and choose this, so that the geodesic from Y to X will go in the. How much the geodesic? I'm not sure I follow the geodesic does not satisfy 5. That's
No, but it is, so
no.
the geodesic is also.
It won't matter, right? Because we have this sort of guarantees that it has to fill all of this path in a way, right? You cannot miss a big part of the. You cannot miss a big part of the geodesic, because then it would mean that you did not actually connect X to Y. Is that what?
I think it was answered, yeah.
Okay, not bad. Good. As long as everyone's happy, it's good. Yeah. So, so this is one idea that goes into the proof, and the next one is we can use this to sort of talk about resolutions. Okay, so right, resolutions. And here we're really sort of starting to see the proof. So again, I have this X, I have G acting on it. So for G, I can just take the pi1 of the 2 skeleton of my classifying space, right? So here I'll have, say, let me just call it K, but this is just, you can think of it as just the 2 skeleton, really. And what I'll do now is I'll, from the action, I'll be able to pull back some kind of structure onto K. So this will be some kind of very singular measured pattern on K. So let's see how this works. So let me use this. The classifying space is always simplicial. They're not stressed it enough. Don't want to log into. No, yeah, it's simplicial. Thanks. Great. Can we all see this board? Yeah.
And yes.
Ah, yeah. Okay. You're pointing at someone else. This is what I thought. It's like this guy doesn't see that. Okay. So here's my K. Okay. Okay. So pi1 is G. And okay. So here's my X, and here is my K tilde. Okay, so we know Gx here. and the first step of this construction is just you map the vertices of K tilde equivariantly to X. Okay, so you can find the map phi. So phi actually goes from the vertices of this thing to vertices of X. Okay, this is easy, right? The action here is phi. There's really no problem building such a thing. The next thing is given an edge. So what I'm drawing now is an edge between some X and Y. I can consider phi X and phi Y over here, and use the bicombing to connect those two with this one chain, right? So I'll do it maybe in this color, orange, I guess. Okay, so I have this bicombing connecting the two. Okay, and what I'll do is that for every edge in the support of this bicombing, I'll just put a little dot on this line. So how many? 10, and I'll arrange them quasi like the way they appear here. Okay, so the closer you are to phi X, the closer those should be to X. Maybe there's sometimes where you cannot decide who's closer, just choose something. And moreover, I'll weight those. Okay, so I'll weight them according to the coefficient in this bicombing. So here there'll be numbers. Something, but that's not a -1. All numbers are positive. Why all numbers are positive? Because I can change the orientation of the edge if they're not, right? So the way I drew an arrow, but I could have chosen the other arrow if the coefficient is negative. Okay, good. All numbers are positive. All groups are hyperbolic. One and we're establishing some really important results there. Yeah, there was a question. I think no.
Reaching the number 6, you just take the sums of the label edges and
this is the one chain. It comes with the coefficients. I just put those coefficients there. Great.
That's going from X to Y, right? Your sequence going from Y to X, it'd be the same picture, but all the arrows would be backwards. That's why I don't care. I can put the numbers positive.
You got it. It's just reading them backwards should mean you're reading that. Okay, good. I have this picture for edges. Next thing is I have the two cells, the two simplices of K tilde, and I'll just do the same picture for each one of the edges, right? So here I have maybe phi of Z. Okay, and there is a bicombing. Okay, I have to decide on the orientation, but you get something like that. The same. They come with coefficients, so on. And similarly, I have something here, and I ran out of colors. Are there more colors? No.
No one here, so you can use red.
If I had a red. Oh, yeah. Yeah. But anyway, on this board, I think it was allowed to use the red. But okay, so.
I think coefficients when they are mapping to the same.
Sorry?
You have two edges mapping to the same edge. You add the coefficient.
There's no adding of coefficients. So for each edge, I have the corresponding one chain. I mark points for each one of the edges I see here, and I give it the coefficient that I see in the one chain. That's fine. This is half, 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 half. And here there should be half, 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 half. They're ordered in some way. That's maybe what bothers us, really. We don't like that. Okay, that's life. And maybe we don't like the fact that I changed the orientation now. From X to Z, Z to X. Fine.
We're using it simplicial here. Like where do you use it simplicial?
So far, I really haven't, but it's nicer to only care about triangles. And that's coming from someone who did mostly cube complexes. Okay, good. Next thing is we want to sort of connect those dots to get a resolution. And the rule for that is you know, if it's the same edge with sort of the right orientation, okay, then you connect those two dots. Okay. So maybe here they're connected, here they're connected. We sort of have the same picture of how they're ordered. And maybe here one of them is connected. Let me put this, I don't know. And here two of them are connected. Fine. They might have, yeah, okay, great. So we're already realizing that there are issues. It's good. What else? There are also things that are not connected to anything. I should also say that if an edge appears in all three of them, I just treat it as, like I cannot choose where to connect it. I just treat it as if I shouldn't connect it. That's fine. Okay, so for those, I'll just put sort of a singular endpoint. Okay, and I can even put a weight here. I'll just put a weight 0 on all of those.
What's the weight of
The what?
the edge does go across? What's the weight of that?
No weight. Put only weights on vertices. Okay. Yeah. So this thing I'll call a resolution of the bicombing to K tilde, And it depends on the choice of the map phi and all sorts of choices that were made during this construction. Okay, great. And here's the here's I really don't have any. You can't start making noises. You said you'll start making noises. Okay, I'll just tell you the punchline. The punchline is, yeah, how do you get the bound? So you get the bound by looking at the total. So you look at the total weight of this measured singular pattern. Okay, so let's call it F. And you prove two things on this, on the total weight of F. I did not define what is the total weight, but you should think of if those are just ones and they do not cross and anything, it's just the number of leaves down here. Okay, so really something like that. Is on the one hand smaller than the number of two cells of K, and on the other is bounded by the volume of X mod G. Okay, and I'll just say two more words to prove this is sort of an done with the accessibility type argument. You want to say that up to choosing the map phi in a different way, you can sort of save on the weight of F all the way down to something that's smaller than the number of two. Okay, so this is sort of, I'll write accessibility, but it's not, I mean, idea. And for this, the idea is that the map from K to K to X sees all of X in some uniform way. And so you'll get at least the volume worth of such leaves. And so this here comes uniform quasi-surjectivity. Okay, and there is your inequality. And I'll stop here. Thanks.
How strongly are you using hyperbolic? I see.
Yes. I'm also using the boundary in one part.
So the weight of like that triangle there, again, it's all the things that didn't get matched up, right? That's what you're.
That's the defect. This is where the defect comes into.
So the weight of the. Okay. What was the total weight of F again? Okay, I'll ask you later. Okay, other quick question. You have this.
One quick question per person. Any other?
You did say something about the full cycle on the boundary. That with this uniform.
This is here, yeah. This is used here.
Where and why is that homology?
Where? Sorry.
Where and why is that homology?
So yeah, I mean, check homology is related to cohomology with bounded coefficients. You want to show sort of the image of this picture here sees all of X, right? So it is a quasi-isometry, so it is quasi-surjective, but the point is it's quasi-surjective with a constant that does not depend on the particular K tilde. So this is this uniform quasi-surjective. And for this, you need some kind of, I mean, I don't know if you need it, but I needed some kind of cohomology class.
Okay, let's so the next talk is supposed to have already started. So which is my fault, not his. Let's have it again.